Welcome to OB's Math e-Pathshala. Today's topic is limit of functions. So please subscribe my channel, like and share and do comments.
Let me start with the discussion of limits of functions, right? So in analysis, analysis is generally it will be the area of mathematics in which we are using various limiting concepts. So in analysis, we are basically using various concepts of limits, and we have already studied of the convergence of sequences, right? Real number sequences. So we have already studied about the convergence of real sequences, that is the limits of a convergent real sequence. Okay, fine. So basically the analysis deals with the fact that it will be the analysis of errors. That means between any two real numbers, how much error you can estimate. Okay, so that is the basic concept of analysis. So yeah, and the limiting process, so that has been introduced in the year of 1680. Okay, in 1680 it has been introduced by Sir Isaac Newton. Introduced by Sir Isaac Newton. Okay, and also at the same time it has been initiated by Leibniz and Leibniz. Okay, Gottfried Leibniz, and their duration of mathematical discoveries was in between 1642 to 1727, 1646 to 1716. So they are quite contemporary pupils in mathematics, and they have initiated to introduce the limiting process. Okay, and that means they had named this type of creations by calculus. Okay, so Leibniz and Isaac Newton, their work was initially unknown to each other, because Leibniz he didn't know about the work of Isaac Newton, and also Newton didn't know about the work of Leibniz, but their creative idea was quite different, and both they understood that to define a notion of function and the idea of quantities which are being close to each other. So they have initiated to define, to formulate the notion of a function. Okay, so they realized to define a precise notion of functions. Before them, people didn't know much about functions, maps, etc. And with respect to these functions, they studied about the the ideas of quantities that are being close to each other. Close to each other. Okay. And yeah. So in the so Isaac Newton, he discussed about limits in his book named Principia in the year of 1687. So in Principia in the year of 1687, so Newton discussed about limits. That means how much the two quantities are nearer by any given difference. Suppose you are giving a real number, suppose whatever it is, suppose a. Now you are calculating the difference between two real numbers, between any two real numbers, suppose x and y. Okay. So the limits to which they approach, so that means yeah. So suppose a be a real, and you are considering reals that are approaching, suppose this is your a, and you are considering real numbers that are approaching a from two sides, from left side and right side, right? So there are two directions to approach a, right? Now with respect to these real numbers, so given any function f, so then how much, so you are taking the functional values of f at these points, suppose these are x, okay, so fx, and how much these fx distant from real number L, so that is of your principal attention to work out. Okay, so how much this difference will be, okay, by giving any real number epsilon. So you need to make this difference less than epsilon, okay, whenever you can find out one real number, some kind of delta, okay, for which, so using this delta you can have two real numbers, one is a minus delta and another is a plus delta, right? Right. So for this real number epsilon, you are having a delta So this must be greater than 0, such that in between these real numbers a minus delta and a plus delta, so the real numbers are approaching towards a, because from the left side and from the right side. Okay. Then we need to check that whether these functional values with respect to those x which are in between these two real numbers, a minus delta, a plus delta. So are these real numbers having a distance with the real number L which will be less than epsilon? So that is your, so that was the main attention that Newton was thinking. Okay. Okay. Yeah. Now at the same time, Leibniz introduced the term function to indicate a quantity. That function, this is suppose a, f. Leibniz introduced the term function to indicate the quantity that dependent on a variable. So they called this x as variable, right? Okay. Okay. And he also discovered the numbers which he named as infinitesimally small. Infinitesimally small. Okay. Right. So suppose you have 0. This is your 0. Okay. So suppose it is 1. This is your half, and you can make as small as you can please, right? Yeah. So given any number, there exists another one which is less than this given number. Right? Okay. So the numbers, so these infinitesimally small numbers will help you to handle the concept of a limit. They are used to handle the concept of limits. Okay. Okay. And after that, in 1748, Leonhard Euler, the remarkable mathematician of all time. So Leonhard Euler, he published 2-volume treatise that has been named as Introduction in Analyzing Infinitorium, in which he discussed power series and exponential functions and logarithmic functions, trigonometric functions, and their intrinsic properties and some more related topics. Okay. And after that, in 1821, Cauchy, he published some papers on analysis, and which has been regarded as an important mathematical exposition for many years. Okay. But the final precise formulation has been initiated by Carl Westers. So precise formulation of analysis that has been developed throughout the years from the time of Sir Isaac Newton. So the precise formulation of analysis had been initiated by Carl Oesters. Okay. And he has presented Oesters, who presented a formal language and rigorous proof proofs. Okay. And the definition of limit that we will be using, that has been given by Oesters. Okay. Using epsilon delta. Okay. So the rigorous, so the formal definition of limit that we will be using, that has been given by Carl Oesters, and we will use this his way of thinking of limits of a function, of a real variable. Okay. Okay. So let us introduce the notion of limit of a function. Okay. The basic motivation to define the limit of a function stays upon the fact that, suppose you have a function f, okay, and you are saying that f has a limit L at the point small a. Okay. Means, intuitively it means that you are thinking of the values, means that you are thinking of the values fx, right, which are close to fx, which are close to the real number L. Whenever you are making x as close to a as we please, that is, we are making x more and more closer to the real number a from left side and right side, right? And technically speaking, whenever we would like to define the limit of a function at the point a, so it is needed that f should be defined at points near to a. Okay. So it is needed to define the map, the function f, at points which are near to a. Okay. Because we are dealing with those fx which x those x that are close and close to A. So for that reason, you need to define f at points. So f should be well defined at the points which are close to A. Okay. Okay. But remember the fact that I am not talking about the I am not talking about that f should be defined at the point A. I am not talking about this, that f must be defined at the point A. The fact is that we are not bothered about the value of f at the point A, but we bother about the fact that the function f should be defined at the points that are close to A. Okay, so I am interested in those fx which are close to A. I am not interested at the value of f at the point A. Okay, so that is not my concern. We are interested in the values which are at the points which are close to A. Okay. Okay, and this makes sense to define the fact that, suppose let us define that, suppose, so let A be a subset of R. Okay, then a point small a belongs to R is called a limit point. A limit point of A of this set. So A is called a limit point of A if so when does it call? For every real number delta greater than 0, for every choice of reals which are positive, you must find out one point, there exists a point x naught belongs to A. So you can find out one point inside the set A which x naught, so that is not equal to A, but such that the distance between x naught and A will be less than delta. Okay, then this point A will be called a limit point of the set A. That means we are considering those points which are close to the set A, because you can choose this delta as small as you can please. However small this delta may be, for those deltas we can find out one x naught which is not equal to A, but the distance between x naught and A will be less than delta. Okay, for example, suppose suppose this is your 0, this is your 1. Okay, now what is A? Suppose we consider the closed interval this. Okay, 1. Now check that this 0 is a limit point. Why? Because whenever you are yeah, so let us take, for better understanding, it is open. Okay, yeah, open. So 0 is outside the set A. Okay, now this 0 is a limit point. Why? Because for any delta, choose any delta greater than 0, however small it is. For any delta, so you will have two real numbers. One is 0 minus delta, another is 0 plus delta, right? So 0 plus delta will be inside this, and it is outside this. So this set contains at least one point of the interval 0 and 1. So 0 minus delta, 0 plus delta, it intersects A, right? And it consists of at least one point which is not 0, right? So there exists one x naught belongs to A, such that x naught is not equal to 0. Okay. So for each delta you can have one such x naught which is not equal to 0, such that this interval intersects the interval 0, 1, where 0 is open, 1 is closed. So that means 0 is a limit point of, so 0 is a limit point of 0, 1, right? Okay. Okay. I think I have already discussed about these limit points in the study of sets in R, I think. Okay. Now we say that for any delta greater than 0, the set A minus delta, A plus delta is called delta neighborhood of A, denoted by VA delta. Yeah. Okay. VA delta. So you can say that. So for any delta greater than 0, there exists x naught belongs to A, where x naught is not equal to A, such that VA delta intersection A not equal to 5. X naught belongs to this, right? Okay. So whenever you are talking about a limit point, you can reformulate the statement like that. And this statement will be generalized to any general setting whenever we are talking about neighborhoods. Okay, fine. Now it should be noted that the point A, that point, you have already observed that that 0 is not in 0, 1. 0 does not belong to A. Okay, so that means the point concerned here may or may not be a member of A. If we consider, if we include this 0 here, then we can consider 0, 1, and in that case also 0 is a limit point. Okay, okay, so a limit point may or may not be a member of A. Okay, but whenever the point A is in the set A, capital A, if A belongs to A, then we do not bother about this point, because we need to find out one x naught which is not equal to A. So that means we need to omit this point from A. Okay, so this point will be ignored whether deciding that whether it is a limit point or not. Okay, okay, fine. Okay, now using this definition you will see that, so suppose that small a belongs to R, be a limit point of a subset capital A of R. Okay, then what do you have with respect to this assumption? So the definition tells us that for every delta greater than 0 there exists a point which is not equal to A, and where does it belong? That point will be in A, x naught. So there exists a x naught which is not equal to small a, and that x naught lies in the set A, such that modulus of x naught minus A is less than delta. Okay, now in particular choose delta equal to 1 by n for n belongs to natural number set. You can choose any delta. So in particular you are choosing these deltas. Okay, then what do you have? Then there exists a point x naught which is not equal to A, but in the set capital A, such that the distance from that point to A will be less than 1 by n. So we are denoting for each n that point as xn. Okay, so there exists xn belongs to A such that xn not equal to A, such that xn minus A is less than 1 by n, right? Now from the theory of sequences, convergence of sequences, you can say that the sequence xn has limit A, right? So the sequence xn is a convergent sequence which converges to A. That means given any limit point you can find out a sequence in the set A which will be convergent to the point A. So thus there exists a sequence in A with xn not equal to a such that xn converges to small a. Okay. In a similar way, on the other hand, if you can find out one sequence, if you can find out one sequence xn in capital A with xn not equal to a such that sequence xn converges to small a. Okay, then what can you say about this small a? Then using the definition of convergence of a sequence to a real number, you can say that for any delta greater than 0, you can find out one natural number n naught such that mod of xn minus a less than delta for all n greater or equal to n naught, right? Using the definition of convergence of a sequence to a real number. Okay, so that means, so you may consider any xn where the indices n are greater or equal to n naught. So choose n equal to n naught. Okay, then x n naught not equal to a such that mod of x n naught minus a less than delta, right? So for a given delta greater than 0, you can find out one x n naught which is in capital A, right? Such that this holds. So this implies that small a is a limit point of the set capital A. So in what follows, you are having this theorem. What is the theorem? That a real number small a is a limit point of a subset capital A of R if and only if there exists a sequence xn in A with xn not equal to a such that xn converges to small a, that is limit of xn will be small a. Okay, fine. Okay, so for example, we have already seen that the interval 0 1 0 1 and any point inside this interval 0 1 are all limit points of the set. Okay, and also note that if you consider in the finite set, that will have no limit points. A finite set will have no limit points, right? What is the reason? Because of this theorem. If it has a limit point, then you can find out Yeah. So you can find out a sequence having distinct members. That means you can find out one sequence xn where xn is not equal to xm for all n not equal to m. Right? So what is the trick? The trick is behind the choice of delta, these deltas. So firstly, you will choose delta equal to 1, then you will have 1 x1, then you will choose delta equal to half, then you will have x2, and so on. Okay? So a sequence of distinct members such that no member will be equal to A, but the sequence will converge to A. Now, since the sequence is in the given set and the set is finite, so it leads to a contradiction because you are having a sequence which is a infinite set. If you think of the image of the sequence, and that sequence lies in the finite set, which is a contradiction. Okay, so a finite set doesn't have limit points. Okay, the set n doesn't have limit points, the natural number set. It is an infinite set, but still it does not have any limit points. Okay, if you consider the sequence 1 by n, then you will see that this has a limit point 0, right? Okay, and so on. If you consider any interval, if you consider any interval, yeah, suppose take closed interval AB, and suppose it is your I, and A is I intersection Q. That means we are considering those real numbers, those rational numbers sitting inside this interval. Okay, then using the density property of the set of all rationals, you can say that so every point of I is a limit point of A. Okay, so this is the set of all rationals in A, in I, sorry, yeah. Okay, so now let us move to define the precise definition of a limit of a map of a function f from a subset A to R at a point small a which will be considered as a limit point of the set A. Okay. Okay. So the definition is like that. So we have already stated that whenever we would like to define the limit of a function at a point A, so So it is very much mandatory to define the function f at the points which are close to A, right? But we are not concerned about the fact that whether the function f is defined at the point A or not. Okay. So in any case, we are excluding that point A from consideration whenever we are talking about limits. Okay. Okay. So suppose let f colon A to R be a map or be a function, be a map where A is a subset of R and small a belongs to R, be a limit point of A. Okay. Then a real number L. A real number L is defined to be a limit of the function f at the point A. Just look at this definition very carefully, that a real number L is defined to be a limit of the function f at the point A if given any epsilon greater than 0, given any epsilon greater than 0. What do you have? You can find out one delta greater than 0. There exists a delta greater than 0. So look at this definition carefully, that you need to place any epsilon greater than 0, any real number epsilon which is greater than 0. And once you choose an epsilon, then you can find out one delta greater than 0, such that if x belongs to A with the condition that x lies in between A minus delta and A plus delta, but x not equal to A. So you can write down the fact like that, that x, those x which are in A, and they will lie in between A minus delta, A plus delta, but the x will not be equal to small a, will never be equal to small a. Then the difference between the functional values at those x which are lying inside A minus delta, A plus delta, but not equal to A, with the given real number L will be less than epsilon. Okay. So that means the real number L will be defined to be a limit of the function f at the point A if given any epsilon greater than 0, there exists a delta greater than 0, such that if x belongs to A with 0 less than mod of x minus A less than delta, then mod of fx minus L less than epsilon. Fine. That means yeah, suppose this is your A, okay, and you are plotting the function on the plane. Okay, then what do you have? Then what do you have? Now suppose this is your L. Okay, then so L will be a limit of the function at the point A. That means, so given any epsilon greater than 0, so this is your L. Okay, so this is your L. This is your L. That means you are considering one interval on the y-axis. So that is your L minus epsilon, L plus epsilon, right? So that means this L minus L plus epsilon is that, and L minus epsilon is that. Okay? Okay? And so if you draw this one, then you will have, so this is your A minus delta, A plus delta. Okay? So taking any point inside this interval, so you are observing that the functional values are still in this one, right? Yeah. Yeah. So that means in between L minus epsilon and L plus epsilon, this. Okay? So that is the motivation behind this definition. Okay? So then you can say that this L is the limit of the function f at the point A. Okay? Fine. So, yeah. So if small l be a limit of the function f at the point small a, then this limit is unique. Unique. Why? Suppose you consider, because if not, then let L dash be another limit of f at a, right? Okay. So then using the definition of limit, so you have two limits. One is L, another is L dashed. Okay. So then for a given epsilon greater than 0. Okay. So for a given epsilon greater than 0, you need to, so you will have a delta greater than 0, right, for the limit L, and a delta dash greater than 0 for the limit L dashed, right? You are having two deltas. One is for L and another one is for L dashed. Okay. So for a given epsilon greater than 0, there exist two reals delta dashed greater than 0, such that, how does it work? So such that mod of fx minus L is less than Now I am considering the epsilon chosen suitably. That means we are considering epsilon by uh, 2. Okay. So actually this delta and delta dash depends on epsilon by 2. Okay. That you can choose. Okay. That is not mandatory, but whenever we are talking about limits and their uh, theorems, we'll using this trick to manage our limits. There is nothing important beyond that. Okay. So this is not a mandatory fact to choose epsilon by 2. You can choose epsilon. You can write down fx minus L is less than epsilon. There will be no harm on that. But to make it more beautiful, we are considering this type of epsilons. Okay. Sometimes it will be epsilon by 3 whenever there are 3 limits, epsilon by 4. Okay. So that is on your choice. That depends on your choice. Okay. So there exists two reals delta delta dash greater than 0 such that mod of fx minus L less than epsilon by 2 whenever for all x where 0 less than mod x minus a less than delta. Right? Right? And then and also since L dash is a limit, so fx minus L dash is also less than epsilon by 2 for all x less than delta dashed, right? Right? So you are having two deltas. One is delta and another is delta dashed. Now what do you choose out of these two? You are choosing the smallest one. Suppose this is your A and this is your A minus delta, A plus delta. And suppose this is your A minus delta dashed, A plus delta dashed. Okay. So in between this A minus delta, A plus delta, this inequality holds, and in between A minus delta dash, A plus delta dash, this inequality holds. Now if you take the smallest delta out of delta and delta dash, you will see that, so what is the smallest? That means the intersection of these two sets, this bigger set with the smaller set. So then the intersection will be the smallest one. So that means you need to choose the smaller deltas out of delta and delta dash, right? And then you define, so set delta naught is the minimum of delta dash. Okay. And in between these two real numbers, a minus delta dot, a plus delta dot, delta naught, these two inequality will satisfy, right? So that means, so then for all x 0 less than mod x minus a less than delta naught, so you will have both the inequalities. Okay. So using both these inequalities, you can have, so mod of L minus L dash. So what is the difference between these two? So this can be adjusted as, so L minus fx plus fx minus L dash. So using inequality, so this is L minus fx plus fx minus L dash. So since these are in modulus, so you can write it as this L dash. Okay. Now what is fx minus L? What is the modulus of fx minus L? Fx minus L is, modulus is less than epsilon by 2. So this is less than epsilon by 2, this is also less than epsilon by 2. That means it is epsilon. Okay. But here you are choosing epsilon arbitrarily, right? You are not giving any fixed epsilon. You are saying that for a given epsilon, that means you can set any epsilon greater than 0. But for any epsilon greater than 0, you will definitely arrive at this situation, that the distance between L and L dash must be less than epsilon, right? But the fact that this distance is fixed, so how could it be less than any epsilon greater than 0? So the only possibility is that this real number is 0, right? So since epsilon greater than 0 has been chosen arbitrarily, so we have mod of L minus L dash must be 0. That means L minus L dash equal to 0. That is L equal to L dash, right? So this proves that whenever the limit of a function f at a point A exists, then that limit is unique. Okay. Okay, fine. So therefore, if L be the limit of of the function f at a point A, then it is denoted by limit of fx equal to L, x tends to small a. Okay, or it can be written as fx tends to L as x tends to a. Okay, tends to or approaches to as x tends to a. Okay. Okay, just give me 1 minute. Huh? Yeah. Okay. So if the limit uh, if the limit of the function f at a does not exist, maybe you can find no L, which will be the limit of the function at the point A. There exists no L. I can give you examples. So if the limit of the function at A does not exist, then you say that, then we say that f diverges at A. Okay.